Most people assume the biggest mistake in an off-grid solar system is choosing the wrong solar panel. It isn't. The mistake that quietly ruins more systems is believing a car battery and a solar battery are basically the same because they both contain lead and acid, and that assumption keeps spreading through misleading product listings and confident internet advice. That shortcut does more than waste money. It can destroy an entire battery bank years before it should fail, and under the wrong charging conditions, it can even create a real explosion hazard inside the cabin, shed or garage that's supposed to give you energy independence. Today we are stripping away one of the most stubborn myths in off-grid solar by looking at what the National Renewable Energy Laboratory (OSHA) and USAID actually say, instead of repeating the claims that bargain listings and random comment sections keep recycling. Anyone building an off-grid system usually isn't chasing gimmicks. You're chasing reliability. You care about cycle life, charging behavior, maintenance, and equipment that will still be working years from now. That's the difference between owning hardware and understanding why it works. Everything begins with one uncomfortable fact. A car battery was never designed to be an energy storage system. Once you hear that, it sounds obvious. Yet this single misunderstanding sits behind countless failed DIY solar installations. An automotive battery is officially classified as an SLI battery. Starting, lighting, ignition. Those three words explain its entire purpose. Its mission is simple. Deliver an enormous burst of current for a few seconds. Start the engine and let the alternator recharge it immediately. That's exactly what it was engineered to do, nothing more. Hours of powering appliances were never part of the plan. Storing solar energy throughout the day wasn't the goal either. And surviving years of daily charging and discharging certainly wasn't the design target. Everything about an SLI battery revolves around one powerful burst of energy followed by immediate recovery. To make that happen, manufacturers use thin lead plates with a large surface area. That design is excellent for producing high cranking current, yet it creates the exact opposite characteristics an off-grid solar system needs. This is where the marketing starts blurring the lines. When two batteries both have 12 volts printed on the label, it's easy to assume they'll perform the same job. Voltage tells you almost nothing about whether a battery is suitable for a specific application. Just like two vehicles having four wheels tells you almost nothing about how they'll actually perform. The National Renewable Energy Laboratory leaves very little room for interpretation. It states, car and marine batteries are not recommended for solar electric system use because they are designed to give a large burst of energy when starting a vehicle and are not made for deep discharges. That isn't a marketing claim. It's engineering. Once you understand that engineering, everything else starts making sense because an off-grid solar system asks a battery to perform a completely different job every single day. Instead of delivering a tiny discharge to crank an engine, the battery stores energy collected from solar panels and releases that energy gradually over time. It repeats that process again and again every single day, and that constant charging and discharging is known as cycling. Cycling isn't a side effect. It's the foundation of energy storage. That's why deep cycle batteries exist. Rather than using thin plates built for maximum starting current, deep cycle batteries rely on thicker lead plates and stronger internal construction, specifically designed to survive repeated cycling. They're intended for renewable energy systems, golf carts, marine house loads, and off-grid cabins, where delivering steady power over long periods matters far more than producing one explosive burst of current. The difference in design philosophy couldn't be clearer. One battery exists to deliver power for seconds. The other is built to deliver power repeatedly for years. From the outside, they may look almost identical, yet inside they are solving completely different engineering problems. And that's exactly why replacing one with the other usually ends the same way. Failure rarely happens overnight. It starts quietly. Capacity begins slipping away. Charging no longer seems as effective. Runtime gets shorter with every cycle, and that is exactly when the internal damage starts accelerating. According to the National Renewable Energy Laboratory, Repeatedly deep cycling automotive batteries leads to several common failure mechanisms, including sulfation, plate shedding, plate corrosion, warping, and increasing internal resistance. What looked like a cheap shortcut slowly turns into an expensive replacement project. Ironically, the people most tempted to reuse old car batteries are usually trying to save money on an off-grid system. The hidden catch is that equipment never designed for daily cycling almost always creates the opposite result. Because you don't eliminate the expense, you simply postpone it. Delayed costs have a habit of becoming much larger than the original investment. Even that isn't the worst outcome. Once charging behavior enters the picture, the conversation stops being about battery lifespan and starts becoming about chemistry. Chemistry is where this myth stops being expensive and starts becoming dangerous. One of the biggest misunderstandings in the off-grid world is the belief that batteries simply store electricity. They don't. Every charge and every discharge is a chemical reaction, and under certain charging conditions, that chemistry produces something you can't see, can't smell, and absolutely cannot ignore. Hydrogen gas flooded lead-acid batteries naturally produce hydrogen and oxygen while charging. Nothing about that is unusual. It's a normal part of how these batteries operate, especially during specific stages of the charging process. The danger isn't that hydrogen is produced. The danger begins when people underestimate what happens if it has nowhere to go. Hydrogen is colorless, odorless, and according to OSHA, extremely flammable. If that gas collects inside a sealed battery box, a compact shed, a garage, or a small off-grid cabin, the problem changes completely because you've created the conditions for an explosion instead of a reliable energy system. Notice the distinction. The battery isn't simply exploding for no reason. The real hazard comes from hydrogen building up inside an enclosed space until it encounters an ignition source, despite what dramatic headlines often imply. That's why the lesson isn't fear, it's design. Proper ventilation isn't an optional upgrade for flooded lead-acid installations. It's part of the safety system itself. USAID states it plainly. Allowing hydrogen gas to accumulate in an enclosed space heightens the risk of an explosion. That single sentence explains why experienced installers spend so much time thinking about airflow before they worry about making a battery compartment look clean or organized. A perfectly arranged installation means very little if the gases produced during charging have no safe path to escape. What makes this even more deceptive is that hydrogen production isn't constant. Certain charging conditions increase it significantly, which means understanding charging behavior matters just as much as choosing the right battery. Overcharging is one example. Charging at excessively high voltage is another. A faulty charge controller can also contribute. There's also equalization charging. Equalization is a legitimate maintenance procedure used on flooded lead-acid batteries to reduce sulfation, but it intentionally increases gassing while that process is taking place. In other words, one of the maintenance procedures designed to help the battery also demands even greater attention to proper ventilation. Experienced off-grid builders understand that relationship, not because it's exciting, because ignoring it creates unnecessary risk. Picture someone installing a used automotive battery inside a cramped enclosure because it was inexpensive, assuming batteries are completely sealed and never thinking about charging behavior. Everything appears normal. Charging continues day after day, hydrogen slowly accumulates, and nothing gives any obvious warning because the danger remains completely invisible. The system keeps operating until something incredibly ordinary happens. A battery cable gets disconnected. A loose terminal creates a tiny spark. A relay switches, static electricity discharges. A metal tool accidentally bridges two connections. According to OSHA guidance, ignition sources like these are enough to ignite hydrogen-air mixtures when the conditions are right. Professionals don't depend on luck. They depend on engineering. They minimize ignition sources wherever possible. They provide proper ventilation. They use charging equipment designed for the application. Most importantly, they begin with the battery that was actually engineered for the job. That's another point beginners often miss. The battery never works alone. Every battery is one part of a complete energy system. Solar panels collect energy. A charge controller regulates charging. The battery stores that energy. Your electrical loads consume it. Every component affects the others. And that is exactly when the math breaks down if one piece of the system is operating outside its intended purpose. Using a battery that was never designed for repeated deep cycling places unnecessary stress on the entire chain. Once that happens, maintenance becomes more complicated, charging becomes less predictable, and reliability starts slipping away long before the failure becomes obvious. That's why the National Renewable Energy Laboratory doesn't recommend deep-cycle batteries simply because they're newer or more expensive. It recommends them because they're built for the operating conditions found in residential solar electric systems. Engineering has never been about making something work today. It's about making sure it still works tomorrow. The irony is that people pursuing energy independence usually value self-reliance more than convenience. They aren't looking for disposable equipment, unnecessary complexity, or expensive replacements caused by internet shortcuts, pretending that every battery is basically the same. That's the real enemy hiding behind this myth. Not renewable energy, not a specific manufacturer. It's the culture of shortcuts that ignores engineering and replaces it with assumptions. Real off-grid resilience isn't built on assumptions. It's built on understanding why every component exists and respecting the limits it was designed around. That understanding is exactly why deep-cycle batteries use thicker lead plates and stronger internal construction. They're engineered for the repeated charging and discharging that defines an off-grid solar system, while an automotive SLI battery is engineered for a completely different mission. Neither battery is universally better. Each one was designed for a different job. Use the right battery in the right application and both perform exactly as intended. Use the wrong tool for the wrong job, and problems that once seemed mysterious suddenly become completely predictable. There's another lesson hidden inside all of this. Most people judge a battery by what it can do on the first day. Experienced builders judge it by what it will still be doing years later. Those are two completely different ways of thinking. One mindset chases the lowest upfront price. The other values reliability, predictable maintenance, and long-term performance because that's what ultimately determines whether an off-grid system becomes dependable or turns into a constant repair project. Flooded lead-acid batteries also demand regular maintenance, and that's part of the technology rather than a flaw in it. They require distilled water, electrolyte inspections, terminal cleaning, and corrosion management throughout their service life. Ignore those responsibilities long enough and charging problems become more likely. Gas production can increase, battery performance begins slipping, and premature failure becomes far more likely than it ever needed to be. Maintenance isn't punishment. It's simply part of owning the equipment. If that level of maintenance doesn't match your goals, there's another reason many modern off-grid systems have increasingly moved toward lithium iron phosphate or LiFePO4 batteries. Current industry trends show growing adoption of LiFePO4 because of their long cycle life and reduced maintenance requirements. At the same time, deep-cycle lead-acid batteries remain a common choice where lower upfront cost matters most. Notice what's missing from that trend. Automotive starting batteries. Not because they can't power equipment for a while. They absolutely can. The hidden catch is that temporary functionality isn't the same thing as appropriate system design. And confusing those two ideas is where many off-grid systems begin heading toward failure. You can make plenty of things work for a short time. That doesn't make them the right solution. The National Renewable Energy Laboratory doesn't recommend against automotive batteries because they're incapable of storing energy. It recommends against them because they were never designed for repeated deep discharges in residential solar electric systems. That distinction changes everything. Combine repeated deep cycling with poor charging practices or inadequate ventilation, and you've moved well beyond disappointing performance into unnecessary safety risks that were completely avoidable from the beginning. The goal of an off-grid system has never been to see how many compromises it can survive. The goal is dependable power that keeps working without demanding constant attention. And that's what separates a random collection of components from a well-engineered energy system. Real expertise isn't measured by how creatively someone ignores design limits. It's measured by knowing exactly where those limits exist, respecting them before they become expensive or dangerous, and refusing to let shortcuts replace engineering. That's the difference between copying advice from the internet and building a system that will still be delivering reliable power years after everyone else is wondering why their battery bank failed.